So this is a follow-up video of the basics and the introduction to trigonometry. This is mostly for year 10s and top ability year 10s, as it's sort of year 10 but also 10A. So we're looking at angles of elevation and depression and then bearings. So we'll have a look at angles of elevation and depression first. So these top images show what the angle of elevation and depression is. So if you have a look, if a question says the angle of elevation of something, it's looking at the horizontal up towards whatever the object happens to be. So, it could be from the ground to the top of a flagpole, that sort of thing. Whereas the angle of depression is from the horizontal down. So think you're looking straight ahead at something and then you look down at the ground. It's the angle between your line of sight and the horizontal. So where you were looking and then now where you are looking towards the ground. An example of this in the real world is standing on the top of a cliff and looking out to a boat that's out on the water. So our first example, I've just changed this example. It did say feet, which is why I've crossed it out to meters. So from a point on the ground, 3.6 meters from the base of a flagpole, the angle of elevation of the top of the pole measures 53 degrees. How tall is the flagpole? Now, given these questions are basically always worded, we always need to draw a diagram. So to start, it says from a point on the ground at the base of a flagpole. So we've got a flagpole and we've got this point out here on the ground. So this is 3.6 meters. Now we're going to assume that in this situation, we're only doing right angled trigonometry. So the flagpole is at 90 degrees to the ground. And it says the angle of elevation measures 53 degrees to the top of the pole. So if we join these two lines, the 53 degrees is from this horizontal part here up towards the line of sight. So that part there is going to be the 53 degrees. And then the last bit of information that we need to put on is our unknown. So it says how tall is the flagpole. So we label our X there. And then from there, we just use our normal trigonometry skills. So the first step when we were doing the trigonometry questions is to label your sides. So if we're looking at this angle here and we go across to the other side of the triangle, that's going to be the opposite. And this side, the 3.6 meters, is right next to the angle. So remember, next to meaning adjacent. So if we have the opposite and the adjacent, it means that we're going to be using tan, because tan of theta is equal to the opposite divided by the adjacent. So again, I will write down here what I know. So the angle is 53. The opposite side is X. And the adjacent side is 3.6. Then we put it into our formula. So it was tan of the angle is equal to the opposite divided by the adjacent. The X is on the top, so the unknown's on the top, which means to work it out, we're going to do multiplication. So it'll be 3.6 tan 53, remembering that we do not have to put the multiply sign between the 3.6 and the tan, because our calculators register that that's what the operation is. So if you put that into your calculator and making sure your calculator is in degrees, you should get 4.8 to 1 decimal place. So 4.8 meters. Now again, it's a worded problem, so you would just need to answer with a sentence. So the flagpole is 4.8 meters tall. And that's that first example of angle of elevation done. So our second example is looking at an angle of depression. So from the top of a vertical cliff, 40 meters high, the angle of depression of an object that is level with the base of the cliff is 34 degrees. How far is the object from the base of the cliff? So again, we need to draw that diagram. So we're going to have a vertical cliff And then we've got the base of the cliff here. I'm just going to shorten that slightly. So here our cliff is 40 metres high. And it says that there is something down here on the base where the angle of depression to that object is 34 degrees. So we're going to draw in our line to here and we can put our right angle in. But what you need to understand is, remember, that angle of depression is from the horizontal down. So it's actually this angle here would be 34 degrees. So it's not actually inside the triangle, and that's a bit of a problem because to solve right angle trigonometry, we need to have an angle inside the triangle. We'll just quickly put the last part of the diagram on. So how far is the object from the base? So we're going to have X here. Now there is two ways you can do this. You can use the properties of parallel lines, and you can see, I'm just going to draw this in yellow. You can see we have a Z angle here, which is an alternate angle, and it means that this angle in here is also 34 degrees. The other way that you could do it to get an interior angle would be that you know that this whole angle here, because from the horizontal and you're standing vertical, that's going to be 90 degrees. You could work out that this angle in here is 56 degrees, and you could go from there. So you could use either angle to solve this question. I'm going to use the yellow angle, so the 34 degrees, and you'll see that again we're just going to be looking at tan, because if we're using this angle here and we're going across, we've got an opposite side and then we've got the adjacent. Now again, we're writing down what we know. So angle is 34, opposite is 40, and the adjacent we don't know. Then we fill in the formula. So tan of 34 is equal to the opposite, which is 40 over x. Now the x is on the bottom this time, which means it is division. So it'll be x is equal to 40 divided by tan 34. And remembering to put your calculator in degrees, it should already be in it, but just double check. So you put that into your calculator and you should get 59.3 meters to one decimal place. And again, you would just have to answer the object is 59.3 meters from the base. And that's the angle of depression example done. Now, I've just done another one. It's a little bit harder, but it is one that a sort of question that is asked quite regularly in a top ability sort of class. So we've got from a plane flying due east at 265 meters above sea level, the angle of depression to two ships sailing due east measure 35 degrees and 25 degrees. How far apart are the ships? So we've got a plane up here flying 265 meters above sea level. So it's flying at 265 meters and it's flying due east. So it is flying this way. Now it says there's two ships that are sailing the same way. So there's ship A here going this way and ship B here also going that way. Now we can put these on a flat line. Wonderful flat line that is there. And then we've got two pieces of information this time. So it says the angles of depression to the two ships. We've got one that's 35 degrees, so I'm going to join that one there, and I'm going to put this angle in here as 35 degrees. But then I'm going to draw in another line in red out to the next ship, and that's going to be 25 degrees. Now we do know that this is at a right angle, and you've got a bit of a complicated diagram now, and it's asking you how far apart are the ships. So it's actually this part that we need to know, which becomes a little bit difficult when you've got quite a few triangles here and a lot of information. So we need to work out what we need to do to get that part. We can't use trigonometry straight away and just do that middle triangle there because it is not right angled, so we can't use that. But what we could do is we could do the large triangle that I'll draw in blue here. We could use the large triangle and we could find this entire distance here, which I'm going to call x. And then we could do the small triangle, and which is going to find from here to here, which is I'll call A, and then we would be able to find y. So firstly, I'm going to do the x value. So we're looking at the big one. Now you can see it is going to be tan because we have got two angles of depression here, and I'm going to find this angle. So I'm following that Z angle, and that's going to be 25 degrees there because you can see on that red line. So 25 degrees, so we've got the angle is 25, opposite 265, and adjacent is x. So tan 25 is equal to 265 on x. And then again we do division. And if you use your calculator, so I'll just write that in, 265 over tan 25. Pop that into your calculator. And to the nearest whole number, you get 568 metres. So then I'm just going to go over to the next page to find A. So if we go, metres. So just before we go to the other side, now I am going to use this angle in here now. Okay, and you can see if we follow this Z angle here, you can see that that angle is going to be 35 degrees. And again, we're just using the 265 and then we've got A. So I'm going to go here, just a second. Okay, so we've got our angle is 35 degrees, our opposite is 265, and our adjacent is A this time because we're finding that yellow line. So we've got tan 35 equals 265 over A. Again, we're doing division, so A equals 265 divided by tan 35. And we pop that into our calculator and we get 378 to the nearest whole number. Okay, so if we go back to our diagram, we have X and we know A, but we were asked to find how far apart the ships are. So to get Y, we're going to do X take away A. So Y is equal to X take A. So we have 568 take 378 to get 190 metres. And then you would end with a sentence, the ships are 190 metres apart. So now we'll just have a quick look at bearings. So bearings are to do with compass direction and things like that. And there's two types. We've got true bearings, which are always written as 3-digit numbers. So even if it's 15 degrees, it's written as 015, or 015, I should say. And what we do is we read a true bearing from north, clockwise from around. Then we've got a compass or a conventional bearing. It depends on which text you're looking at. And these are read from either north or south towards the east or the west. And I've given an example there of what one might look like, and it is north 40 degrees east. Whereas you can see in the true bearing, it's just 265 degrees T, which is true. So our first examples are just reading compass bearings, and then we'll go into trigonometry with it, just for one example. So the first exam, we're going to do a true bearing and then we're going to do a compass bearing for each of these. So for part A, the true bearing is going to be read from north all the way around to this line here. Now, it hopefully is assumed knowledge already that you know that there's 360 degrees in a circle. So going from north all the way back around to north gives you 360 degrees, which means each point, so from north to east, it's 90 degrees, from east to south, 90 degrees, and so on. So from north all the way around to south, that would be 180 degrees, and then we have to go 50 more. So the true bearing would be 230 degrees true. Whereas for the compass bearing, what we look at is the bearing in this top half? And if it's in this top half, we're going to read from north. If it's in this bottom half, we're going to read from south. Okay, so I'll just get rid of those now. So we're reading from south. So we're going to start with south. And then we look at how far to the west it is. Now, it's got to be read from here around. So it's going to be south 50 degrees west because it's going towards the west. For part B, it's a little bit different. Firstly, for the true bearing, we're reading from north to this line. Now, the 30 degrees is for this part, not for the part where I've drawn the red arrow. But we know the whole thing is 90 degrees because from north to east it's 90, which means the red arrow would have to be 60 degrees. So our true bearing is going to be 060 true. And then when we do our compass bearing, we can't write east 30 degrees north because that's not correct. We have to read it from north or south. Now it's in the top half, which means we're reading from north, so straight away we can write north. But again, we've got to read north towards the east, which means instead of writing 30, it's actually going to be 60 degrees east. And that's two examples of writing bearings. You will need to know how to draw bearings as well, but if you can know how to read them, that hopefully will help you draw them. So we'll just quickly do an example of bearings with trigonometry. So a hiker walks on a bearing of 125 degrees at 6.5 kilometres per hour for half an hour before stopping for a quick drink. How far south of the starting point is the hiker? So, a couple of things. We need to draw a diagram. Now, I always start just by drawing the compass because then I can draw my diagram on here, and then if I need to, I can draw it a little bit bigger later. So, 125 degrees. Well, from north to east, it's 90. So we're going to go out this way, and this whole thing here is going to be 125 degrees, which means this little angle in here is 35 degrees because it's 90 to there and then another 35 to get to 125. Now, it's asking you how far south this hiker has gone. So straight away we know that that's X, and we've got a 90 degrees here. The last part of information that we need to work out, it says they're travelling at 6.5 kilometres per hour, but they only go for half an hour before they stop, which makes this line here, and I'm just going to move it out to here, this line is going to be 3.25 kilometres. Now, we do have one other problem. That 35 degrees is not inside the triangle at the moment. But we could make it inside the triangle. Again, we have got a Z angle, so we can also say that this is 35 degrees here. And now if we label our triangle, so if we go across, we've got the opposite and the 3.25 would be the hypotenuse. So, to answer our question, opposite and hypotenuse is sine. So we can write down what we know if you want to, otherwise for this one we can go straight in. So sine of 35 is equal to the opposite, which is x, over 3.25, which is the hypotenuse. So then we have x on the top, so it means it's going to be multiply. So 3.25 times sine of 35, and on your calculator, that gives you 1.86 kilometres. So then you would say the hiker is 1.86 kilometres south of their starting point. Okay, yes, they've walked out on that bearing, but if we're just looking at how far south they are 1.86 kilometres. Hopefully that has given you a bit of insight into the further applications of right-angled trigonometry.